Yeah, so I should begin with a couple of apologies for this. These are all fresh slides, mostly fresh slides. And what I'm going to talk to you about isn't a technical talk. Really, there's going to be some technical meat toward the end, maybe if we get there. But by and large, what the talk is going to be about is exactly this plea to make train systems, or sort of systems that have machine learning at their core, substantially easier. From that description, you may think machine learning is going to play a central role in this talk. It will play almost no role. Okay? And the pitch of what I'm talking about is that sort of the next gap or the next breakthrough in machine learning and deploying machine learning techniques has nothing to do with machine learning. It really is a database, programming language, software engineering type of problem. And we've been working on these things for the last couple of years. And so I'll explain to you why I think that's the case. So these things we're calling trained systems. Really what I'm using is a way to say a system that answers queries over data that's sort of much, much less structured than traditional relational queries. And somehow uses machine learning to do it. So these are systems like Watson or Knowledge Graph. And I'll give you some examples in a little while of what I mean by trained systems. Really things that use machine learning. Now, I would argue that these systems, if you're just a systems builder, represent some of the most interesting systems in all of computer science. And I'll argue for that in a little while. The reason they're interesting, not only just to computer science, but beyond, is that they've captured the public imagination. So Watson captured the public imagination in a way that few systems ever have. We'll come back to that. So these are a class of important and emerging systems, and I think there's going to be many more. Now, of course, there's a bunch of sort of statistical smarts that goes into building one of these systems. But I argue that that's actually not, the whole part of the challenge. And anyone who works on these systems for any appreciable length of time will tell you building features, you'll see feature engineering, sort of figuring out the signals that you're going to put into the statistical model, takes way more time and effort, and where more of the manpower goes, than any of the underlying statistics. So feature engineering for all of these systems is a really big challenge, and that's what I'm going to spend most of my talk telling you about, is what is the pain points there that we've seen in the examples both in the published literature and in our own systems to try and understand this. Now, the reason we're studying this is because these trained systems, they've been fantastic, but they've been these really high-end applications. They're things that are built by Google or IBM's Deep QA team, but they're not out in the commodity space. People can't download a Watson and try it out, although IBM is trying to sell them. Now, if these things are going to make an impact beyond these very high-end applications, they need to be substantially easier to engineer. And again, the pitch here is that substantially easy to engineer has nothing to do with making machine learning work faster or easier or better. It really has to do with traditional sort of data manipulation, sort of code slinging challenges. And that's what I'm going to talk about. Okay. So first what I'm going to do is I'm going to walk through some popular trained systems that are out there and sort of explain the lessons that have been published about them. Then I'm going to show you demonstrations of our systems in this space that have been running for the last couple of years that started in some of the DARPA challenges. Then I'm going to give you one little technical nugget to show you something that's logistic regression, to ground out what it means by training if you haven't seen it before. Precisely what it means when you have some features and you want to learn a model. And that's only going to be about 2 slides. Now it turns out this model is extremely simple, but it's actually the model that's under a lot of these big high-end systems, which has been known about for 60 years. So it's difficult to say that machine learning is really what's advancing. Finally, I'm going to tell you about the challenges that we see, the challenges that I'm going to try and articulate for you around feature engineering that makes it sort of uniquely different as a software engineering task or as a data engineering task than other challenges. Okay, so let's walk through a couple of these great trained systems that have been out in the public eye. The first one is Google. Right? Google is essentially a trained system. So you enter some query like University of Wisconsin, and you get back some both unstructured things like documents that represent the University of Wisconsin, and now after about January of last year, you start getting back structured information as well, which is a project called Knowledge Graph, which is very, very cool. Now, if you take your IR course, they'll tell you, okay, well, there's all kinds of things you need to know about how the things are retrieved, the pages are retrieved. Well, they use PageRank and they use TF-IDF. These are 2 very valuable signals to get back the answers. But that's not, all of what goes on there. Actually, the features, at least circa 2009, the number of features that they were using to push back that search result was in the 500s, it's actually in the thousands they project now. These are features about personalization, context of the search. These are all the different signals that are out there about you, who you are when you're searching, and also about the page. Okay? So it goes well beyond sort of PageRank and TF-IDF. It really is this learn, train system. And in fact, in the Wired magazine article, when they're interviewing people in the search team, if you go talk to them, they'll tell you about this sort of relentless slog to keep adding in features to the system, finding new signals that they can do to improve search quality and thereby improve ad placement and all those kinds of things. Now, I don't know how all these systems are built. I don't know all the internals of Google search. But you can take away a lesson from this. Even the most tech-savvy organizations among us, Google as one, even for them, feature engineering is like, these are what all the published reports talk about, how many people are just sitting around slinging systems. Let's look at a second example. So probably you all remember this from a little while ago. This is Watson after it has beaten Ken Jennings at Jeopardy, and, had a 3-day stomping of human competitors. Now, Watson was a great project, and the Deep QA project that they're trying to basically turn this into a product at IBM generated a huge amount of interest, right? It generated a Super Bowl ad, but it actually also introduced the popular, basically all of everyone, the public, into the idea that machines could reason statistically about facts. So people before that kind of knew that you could do statistical regression kinds of things, CEO, CTO type people. They kind of understood that you could take in a collection of numbers and kind of make a prediction about it. But reasoning about facts, raw facts about what the right answer to a query was something that blew people's mind. And so these little display that they had, which would say, we think it's albinism with 98% confidence, actually kind of resonated with the public. And there was a huge amount of excitement around that for this reason. And I will say that I have been in meetings after this, talking to people. And IBM people will tell you the same thing. Just the level of awareness of what a machine can do now has grown tremendously. And it's not just business processing, it's not just data processing, it's answering these questions. So one of the great things about Watson was not only did they have a tremendous sort of wonderful success, they actually came and were very open about talking about it. So they published this great paper, Ferrucci and those guys, and published a thing called Building Watson ODO Deep QA. Now, I remember when they came to the machine reading kickoff, they were funded on this program called Machine Reading, which I'll talk about our project in a second. And they came in, they gave a talk, and actually the reception in the audience was kind of interesting. So people on one hand were very interested in what they had achieved, that they were able to win at Jeopardy and sort of this triumph of AI, if you like. But on the other hand, people were saying, well, it's not really AI, because what they're doing is sort of this logistic regression with a whole bunch of features. So you can start to see that theme emerge. And so what I'm going to illustrate to you here is sort of how they categorized, how they went about this, and that actually feature engineering is where they spend a large fraction of their time. Again, saying that it's a pressing challenge. Okay, so I think this graph is just fascinating, so I'll explain to you what's going on here. So this graph on the x-axis has a percentage answer, so these are for Jeopardy games. They're going to plot every Jeopardy game. And then the precision, that is when you actually ring in and get called on, how often are you correct? Each one of those points up there represents an actual Jeopardy game, okay, the winner of the Jeopardy game. If you can make it out, it's very hard to see, but there's sort of some dark dots. That's Ken Jennings. He's the grandmaster. You can see he answers some of the questions, some huge fraction of the questions more than everyone else. And in fact, they speculated that he was sometimes ringing in even before he saw the question. Right? He wasn't even processing the question. He was just, as soon as the light went off, he would click and trust himself that he was going to be able to answer. And he also has a stunning precision. Now these lines here are basically, and it's not important what they are, they're really basically just two baselines of the Watson system when it was first constructed. You can see they have a long way to go along this curve before they're going to be anywhere close to those competitors. So this is the winner's region. Now they spent, on this project, so this is when they started, about 20 engineers' time, 3 years on this project, essentially full-time. They basically came up with hundreds of ways to answer each one of these questions. And over time, what they did is increase exactly that recall. And what they were doing, if you go to like James Phan's talks and hear about it, is they were adding in more and more features, more and more ways and signals of answering these questions. So one lesson that I will try and come back to and substantiate a little bit more is there's sort of this strange thing that happens when you're building these trained systems, when you're building these feature engineered systems, which is basically the more the merrier. And this is not true in traditional software engineering, right? If you start adding in more and more features, you risk breaking other features. You start adding in more and more different data structures, eventually they're going to have some sort of legacy problem. But here, you're allowed to get away with essentially a very loose coupling, where people are throwing in features continually. So it has sort of an interesting software engineering. To echo that point even more strongly, the last sort of trained system that I want to talk about is Netflix. So the last of the public systems. And this is a long quote. But the message of the long quote really comes through at the end, which basically says the more people joined, the more the resulting team score would increase. And what they're saying is that people with some good ideas and some bad ideas were able to put their systems together, if you know the end of the Netflix challenge, and basically build the strongest system. Now to me, this is very interesting because it suggests a different way to design this kind of software than people have thought about before. You're not building these sort of rigid interfaces. You're basically trying trying to take advantage of all the possible signal you can and just pump it into the system and let the statistics do it. All right. So, with that, I want to tell you a little bit about some of the systems we built in this space to explain how we have seen many of those same lessons pop up in our work. I should plug that all of these things that I'll talk about have overviews on our YouTube channel, so you can watch 4-minute overviews, and later I'll play you some creepy Siri voiceover thing of one of our new projects. So, our project Deep Dive was a DARPA-funded project that was funded on this thing that the idea was to build a system that was able to read a large corpus of text and then answer sophisticated questions about it. Watson was also partly, I mean, they had a huge amount of funding, partly funded on this project as well, so it had kind of a similar flavor. You weren't told too much about this text corpus. It was substantially less structured than something that would say, you know, here are some relations, answer some questions about it. For example, this was actually a question from the evaluation. You would answer things like, list the members of the Brazilian Olympic team in this corpus along with their years of membership. Now, ahead of time, you weren't told that you were looking for Brazilians. You were told you were looking for people, places, and things, geopolitical entities. And you were told you were looking for organizations and their relationships between them, like who's a member of. But you didn't know specifically you were looking for Olympians or Brazilians. You also had to do some temporal reasoning and prove that you were able to say something like, if I say that this person was on the Brazilian Olympic team in this corpus, I want to prove from that text. I don't want to just have some random, free-based answer. I want to actually reason from the text. Okay, so we built this thing. We did quite well at our evaluation. We were very happy with it. But for various reasons, we decided that we were going to build a demo out of this that went beyond just answering these type of questions. And that's what I'm going to show you right now, is that demo. So the demo we decided to build was basically extending Wikipedia. Okay, so we were going to take Wikipedia, which is a nice structured information source, we were going to supplement it with huge volumes of text and fill in facts and relationships of the kind that we just saw. Instead of doing it on a small test corpus, we were going to try and do it on the entire web. Now, all of the challenges essentially that came up during this, there were some challenges that were sort of natively machine learning, but most of the challenges that came up actually were in this feature engineering. So the idea of why this would be interesting is Wikipedia is a very high quality information source. The facts are entered by people. They tend to be correct most of the time. But there's a huge amount of data that's not anywhere inside Wikipedia. That's generated by people on web pages and tweets, all kinds of weird events, videos, photos, and blogs. And the idea was take the machine reading system, read that stuff, and see if we can prove those textual answers for things that are in Wikipedia, and actually even extend. So I'm going to show you that demo in 1 second. It's available on the web. You can definitely play with it. The key, though, that I want to get across is that it had some scalable probabilistic inference thing, but it was really about getting the best of breed of all the tools and being able to sling them together efficiently. And the lesson that we learned after building this, when we started, we thought it was going to be about smarter machine learning, taking advantage of weak information sources and correlations. But after we built this thing over a couple of years, we realized that all it was really about was picking good features. And being able to very quickly figure out that a feature was helping you or not and put it into the system. And it's not that we did this and got sort of some kind of mild quality improvement. We actually got state-of-the-art quality on benchmark results just by doing this. Okay? Just by selecting features in a very rapid cycle. And all the demo that I showed you was built by 2 graduates. All right, so let me show you this demo. So this is an old version of the demo. There's a new version that's linked off the webpage. This is from 2009. What this is the Wikipedia page for Barack Obama. And what we've done is we've run this over a small crawl. This is actually the NSF Clue web crawl, the CMU Clue web crawl from 2009. So you'll see some outdated references. So there's Barack, and we've added this little text box at the top that says, how many times we found Barack in documents and sentences and videos and inside different content. Now, to show you that it is doing some kind of deeper analysis than just sort of surface level string matching here, let me show you this one thing about Hillary Rodham Clinton. So you see the entities here that are related to Barack. Since this is 2009, it was sort of around the election. So there's Hillary Clinton, John McCain in the U.S. These are things that were frequently mentioned in news articles. Now, one thing I want to point out from here is that this line right here says, has he forgiven Barack for trouncing good old Hill, otherwise a shoo-in for heading the demo ticket into this election? Now, the system is using this sentence to prove that Hillary Clinton and Barack Obama are related. Now, to do that, it has to figure out that Barack is actually Barack Obama. That one's not too hard. If it's a Barack mentioned on the web, it's usually Barack Obama. Good old Hill, though, it's a little bit trickier. There are tons of Hillarys that are out there, and that's a nickname actually for Hillary Rodham Clinton. Now, actually, what it's done is actually resolved even more. It's figured out that he here is referring to Bill Clinton, okay, from context that's in the rest of the article if you dive in. And then it's using that sort of statistical evidence that that's actually Hillary Clinton. So it's able to do some very, very sophisticated reasoning. It uses a bunch of NLP tools underneath, but it's basically just finding those good features that allow you to conclude who these entities are talking about. Now the next thing I want to show you is that we can do the same thing inside video. So what I'm showing you here, these are the sort of relationships. So there we were just saying these are entities that are inside Wikipedia. Now we can talk about relationships between those entities. So now what I want to do is just offer provenance that Harvard Law School and Barack Obama are in a relationship, in a specific relationship, that Barack attended Harvard Law School. So I'm going to play you a video that Deep Dive, or actually it was called Whiskey at this point because it's an old demo, believes substantiates this claim. Okay, so wait about 10 seconds.
10-year-old Gabriel sees a man from a mixed marriage running for president.
I think he's really cool because he looks kind of like me, and he's elected. I feel that I could be elected to president too.
They have something else in common too. His mother is from Kenya, just like Barack Obama's father. And his parents, like Barack and Michelle Obama, went to Harvard Law School. But
so that is actually video provenance that says, in that video clip, we found evidence that's out on the web that actually Barack went to Harvard Law School. Okay? And if you're worried that there's some parlor trick here, that we're just proving facts that are inside Wikipedia, I encourage you to go to the new page where we find all kinds of crazy false facts, but I'm not going to walk through the rest of that. But things that are actually textually substantiated. We don't make any claims about veracity, but people have spread rumors, and we report those rumors just as well. So please go ahead and take a look. For our purposes, what I care about getting across to you, though, is that actually, actually, the state-of-the-art quality, bridging together all of these different things, getting information extraction actually out of video and audio, getting all those different features together, was really a matter of feature engineering. A lot of the smarts went into that. Now, we did have to do a bunch of work on the scalability side to get it working and get it off the ground. That was very valuable work. But what I'm arguing really is that scalability is not the most interesting challenge in machine learning. It's actually, I think, the ability to build these systems efficiently and get more signal to them. Being smarter with machine learning got us some little distance. Being smarter with features got us a huge world of difference, just like the Watson guys when they were adding in more of those features. To bring that home, these are the challenges that actually we had to face. You don't see machine learning really anywhere. Web crawling, information extraction, deep NLP, okay, that could be machine learning. Audio video transcription, parallel joins. Actually, most of the time doesn't go into probabilistic inference. It actually goes into a big parallel join that takes every mention on the web page and puts it all together. It's actually run over a big 100-node Greenpone cluster. Since then, the data has expanded by a huge amount. You see, it took about 500,000 machine hours to create the initial demo. We're well into the millions now, so that's all like workflow system stuff. Old classical stuff. We were using crusty binaries from the 80s to do a lot of this. System architecture, magic happens is the only part that machine learning occurs in. Okay? The rest is standard stuff that you know how to do. Okay? So it's all, like most of the challenges are everywhere else, just magic. Okay? And I'll show you the magic in a little while that actually works up to a first fraction. Now what I told you was that we wanted to build these high-end systems, and that was great. Google and IBM's of the world, you can pay them and their consultants to come in and they'll build it for you maybe. Google is happy to spend all of the best engineering talent on building these trained systems. But if these things are really going to have a transformative effect, that is, people are going to start building fundamentally new types of systems, then building them has to become a lot easier. And so one of the thrusts of my research is actually exploring those challenges around making high-end data analysis a commodity. Something that you could eventually buy like Oracle or get free like MySQL and just set up and build interesting applications. So that's the direction we've been pushing. Away from the web scale freaky, we have a huge number of machines and look how fancy we are, to something that could actually be useful to end users. So with that, we're going to do a creepy Siri voiceover about this project called GOG Deep Dive, and it'll explain what it is. And then I'm going to I'm going to show you GOG Deep Dive, what it is, it'll explain why it's useful. Then I'm going to come back to show you what I think is the single most useful feature that we built for it, that has absolutely nothing to do with machine
GO
learning.
Deep Dive is a collaboration between Shannon Peters' Geoscience Research Group and the Hazy Research Group. The goal is to help geoscientists extract data that is buried in the text, tables, and figures of journal articles and websites, sometimes called dark data. To bring dark data to light, we use the Hazy Research Group's machine reading system. The GO Deep Dive system extends a database created by Professor Peters' group, called MacroStrat. MacroStrat contains information about rock formations and individual geographical units. Here is an example, the Barnett Formation. The Barnett Formation contains several units that are spatially distributed, as shown on the map. It is also temporally distributed over several geological time intervals. MacroStrat contains over 36,000 rock formation units, like these. There is also geologically relevant information in journal articles like this one. As we'll see, GO Deep Dive extracts information about these rock formations from journal articles. As of today, GO Deep Dive has processed over 20,000 research papers. This is the GO Deep Dive homepage. It shows a summary of the results of GO Deep Dive's deep linguistic and statistical processing. GO Deep Dive has two main goals. First, organize the literature around the MacroStrat database to create a spatio-temporal index of the geology literature. On the left-hand side, we organize the extraction results spatially on a map. Our second goal is to augment the MacroStrat database by extracting dark data. On the right-hand side, we list some global statistics. For example, we found about 400,000 mentions of formation units from 20,000 documents, and about 27,000 measurements of the units. Let's walk through an example of how a geoscientist may use GO Deep Dive. Suppose the geologist is interested in the Barnett Formation. We can navigate to that formation from here. Just as on MacroStrat, GO Deep Dive reports 8 units in this formation. Each unit is characterized by a polygon on the map, and their canonical names are listed in this table. We also show the extraction results for each unit, including the number of mentions, documents, and measurements. Suppose the geologist is interested in the first unit, the Barnett Formation at Fort Worth Basin. We can navigate to that unit from here. This is the page for the unit of the Barnett Formation in the Fort Worth Basin. On the left-hand side, we embed a page from the MacroStrat database. In the sidebar on the right-hand side, we show some statistics about GO Deep Dive's extractions for this unit. For example, the estimated total organic carbon, or TOC, is about 32%. This information does not exist in MacroStrat. Instead, it is aggregated by GO Deep Dive from dark data, that is, the data buried in the text and figures of journal articles. The geologist can dive deeper into how this number is produced. Here, we have organized the extracted measurements along different dimensions, including time and space. Suppose our geologist wants to dive into the temporal dimension. By clicking here, she is presented with a list of time intervals for which GO Deep Dive has found extractions. Here, Pennsylvanian and Osage. Click on the first button, and GO Deep Dive will load all the extraction details about the Barnett Formation at Fort Worth Basin and in the Pennsylvanian time interval. Each row in this table is one measurement extraction. We show the annotated textual evidence for each piece. The geologist can go through them and provide feedback on their correctness. For instance, the first extraction appears correct, and so we click yes. Such feedback helps GO Deep Dive improve itself over time. We can dive even deeper into the document context of this sentence. This is GO Deep Dive's document browser. A journal paper is anatomized by the different types of entities it mentions, as well as colorful annotations for these mentions. Move the mouse cursor to hover on one of the mentions, and you will see a box containing further information about this mention. Here are 3 kinds of probabilistic predictions about this Barnett shale mentioned. Notice that Fort Worth is not mentioned in the surrounding text. Using a rich variety of signals and background knowledge, GOG Deep Dive determined that this text referred to the Barnett Formation located at Fort Worth Basin, and not, for example, any of the other 7 units in this formation. The geologist can provide feedback for these predictions as well. GOG Deep Dive is a quickly evolving project, and we have been continuously expanding our data sources and enhancing the signals and features. For example, a feature that we recently added is called table extraction. These extractions are from tables in the journal papers, instead of English sentences. Still, we can dive into the source table. Those highlights indicate the formation name and the measurement value. As you can see, there is a huge amount of information in these tables. In the coming weeks, we will begin to extract even more of this rich measurement information into GOG Deep Dive. Thank you for your interest in GOG Deep Dive. We would also like to thank all of our sponsors and collaborators who have made this project possible. Thank you and stay tuned.
So again, this is actually something that is in collaboration with Shannon Peters, and it has a very classical commodity feel, right? Just to point it out. There's a database, a very simple structured database, which is this MacroStrat. It's actually a Postgres instance, and he wants to hook it up to all the literature that's out there. This is exactly the problem that a lot of companies have today, where they have their structured database that they know about, and they want to hook it out there. So this is one of the reasons we're working on this, and Shannon's an awesome guy. Now, machine learning stuff plays a role, so I want to be very clear here. Machine learning is very useful. There's a lot of interesting work that's going on here. But most of the challenges that we faced, and by far what differentiates the quality and how quickly we can turn these systems around, has to do almost exclusively with software engineering. And to make that point, I want to show you this feature that I promised you, which has nothing to do with machine learning and looks totally stupid, but is by far the most effective thing we've built. Okay? All right. So let me show you this. Okay. All right. So this is actually when we started. We started in the end of July, or I guess the beginning of July was the first measurement. So this is when the project started. Okay. So you saw the demo. If you're clever, by the way, and look at the video, you can figure out the URL, but it's not quite public yet. We're going to make it public at the end of the year. The geologists are looking over it, making sure it's not making crazy mistakes. Okay. So what we did here is rip off timeline. Okay. And we had a very simple thing that said, for example, we started with a very initial carbon extractor, just trying to find those carbon measurements. One thing that maybe wasn't clear from the video is that geologists now only have a micro view of the world. They can know the carbon measurements that they've acquired, and maybe a handful of others. And so they were acquiring essentially these things by hand. What we want to do is get this macro view, so extract all of the carbon measurements and figuring out what's going on at this macro view. That's why it's called MacroStrat. So we started, and you see the scores. Okay, so this is a stupid little populated spreadsheet. Says, oh, we have precision at 0.6 and F1 score. Now the point is that every time we gave them some little tool like this, and we're actually showing it to them, so they can see how well we're doing, attaching times to intervals, whatever it is. Each one of these things. This is actually a little bit old. It stops in July. It stops in August. So the point is here. So now, just fast forwarding here, we're able to get the formation, the end-linking on the formation up to 0.9. And you see there's some comments. This is Shannon, the collaborator. He's starting to write rules and give us feedback. His rules now are up to 0.9 because we don't know anything about geology. We can't tell the right answers from the wrong answers, but we can score them with some help. To, I guess, August 22nd. So this still isn't the live version. But you see that now we're able to extract those entities with precision 93. Our recall is about 40%, so we're still missing some mentions. We still have some quality to improve. But the point is, when you get into the 90s, almost everything you're looking at is correct. And I think our internal numbers are a little bit higher right now. Once you get into that 95, 97 region, basically everything you look at in a browsing session is correct. And so you start to trust the system a little bit. And that's the threshold we want to get to. But my point is, the two things that made our progress sort of skyrocket, and our quality skyrocket in these things, nowhere on there was machine learning mentioned. Okay? Nowhere on this timeline. It was just getting in more signals, just writing simple extractors and simple rules to pipe into the system. And actually our framework now is basically taking scripts that are in all kinds of languages. So we started originally, we had this very formal language in AI, thing called Markov logic. It's basically data log plus weights. No one could write it. So then we said, okay, we'll make a version of it instead where it's Python, and you can just tell us some signals, and we'll do our best. The more you give us, the better, but we'll just do our best with whatever you give us. Okay, it turns out people don't want to write Python either. So it turned out that these guys, for whatever reason, had learned PHP. We're actually writing extractors in PHP. That seems a little perverse, but we can use their stuff. So actually, their rules are written in PHP. We don't care. It's basically a bunch of relation-to-relation maps that we run. It runs behind on some workflow system. We don't care. We get more information out. Okay? Now we're trying to encourage them gently to write with tools we like so we can help them out a little bit more. But the point is, all those challenges that I'm just talking about, the ones that actually got it off the ground, none of those were machine learning challenges. Which is actually a great credit to machine learning, that they have built a set of reliable tools that people can use. So the lesson here that we learned, by the way, everything sits in a virtual machine except for the deep back-end parsing. So if there's anything in here where you think, oh, I have a better way to pick something, I'm sure you do, I'm sure you're right. That's actually what this is about. If you have a better way to do any part of that pipeline, we're happy to give you everything because it's all open source stuff and you can improve it, but please contribute it back. Okay, the lesson that we took from here was that basically the rapid evaluation and feedback made a much better product. Okay? And what I mean by that is typically in machine learning, there's a sort of lag. You have an idea, you want to add in some signal, and then there's a lag until you figure out if it made any kind of impact. That whole cycle that's in there, which really seems to determine how high quality your signals are, has very, very little to do with machine learning. The machine learning is already scalable enough. It's all the software engineering, programming, writing the extractors, debugging, all that stuff that goes around. Okay, so the takeaways are, the first high-level claim, the schema, the argument really is, if training systems are going to become a commodity, which you may think there's no reason for them to become, and that's fair enough, but if they are, and I argue that feature engineering is one of the things that needs to become substantially easier. Feature engineering has a bunch of remarkable traits to it. The first is this more the merrier property. This loose coupling property is really phenomenal. It means that you don't have to worry too much about correctness. You can throw in all kinds of things. This doesn't happen with a logic program. You start adding things in, they get a little bit fragile once they get to a certain size. But here, because they're sort of only statistically coupled, you can throw in a huge amount of code. And this is sort of a nice dream for sort of software engineering. I put here kind of aggressively that man months are no longer mythical. If you're familiar with the mythical man month, really, you put more people on the project, it seems to get better. Now, of course, I've tried this with 2 graduate students, 1 collaborator, and 1, I think, postdoc on the geo side. So we're up to 4. Our scale isn't very high. But it looks like you can actually keep adding people and keep getting success, which is not something you can do with a typical software. Okay, so now all I want to do, I'm going to give you something, a very brief technical interlude, basically about this more the merrier, because I want to ground out, because maybe it seems pretty abstract, like what does machine learning mean in this context? And I'm going to give you an extremely simple model, and in fact, a model that works. Okay? In fact, it generates most of what goes on in GOG Deep Dive. Then I'm going to talk about what kind of system we would want to exploit those problems. So the background, this is the only sort of math-ish thing in the talk, but I want to ground it out for you. I'm just going to show you very briefly what logistic regression is, formalize it for you, and then you'll see that it's really not scary at all. So first, the setup, and then how we actually use it in GOG Deep Dive. So the setting is, in this problem is, we're given a set of objects, O1 to O capital N. We have some label, and that label will capture some class we're interested in. Okay? Later we'll see an example label will be something like, this pair of mention and entity are actually referring to one another. Some Boolean proposition about the universe you care about, and you have some labels. Okay? We'll talk, if you want, I can talk more about how you can acquire those labels if you think those are expensive, which I would disagree with you vehemently, but I'll tell you about it. Okay? The feature functions then are these F1 to FD, and basically each one of those is just mapping to 1 minus 1, or 0, 1, it doesn't really matter. For a very strange, awkward bias, I write 1 minus 1. The objects are only accessed through their feature functions. Okay? So you take the object, and you write all these signals about it. Okay? It's a noun. Anything you can think about it, and you push it into the system. That's the mentality. Now, it turns out, with some nice statistical theory, that any W that's of D, that size D, defines a probability distribution. Okay? And this is what logistic regression is about. This is one of a class of length functions for regression. Since the probability O takes label 1, that's true, let's say, is equal to sigma, where sigma is this funny looking function here, okay? Accessed by a dot product. This is meant to be a dot product. So basically it's a weighted combination of features put into some exponential. And if you don't know what this function looks like, it basically looks like an S. Okay? That's what this guy's like. So you have a sort of nice, interesting linear region, and then you have, like all exponentials, you have a linear region, then you max out in 0, 1. And actually, you can read the numbers that come out of this as probabilities. All right. This is one of many. If you like, offline I can rant to you why this is a very good choice, why logistic regression, even though it's been around for like 50 or 60 years, is still the most popular thing and the first tool that comes out of almost every person who now calls themselves a data scientist. It's the first one they try, because it works. It really works. Okay? And the numbers are meaningful. The probabilities are meaningful. You can actually reason with them and debug with them, but I won't unfortunately have time to do it. Okay, one word about W. So how do we pick W? It's very simple. This is what the learning component is, actually, what they say when they say machine learning. Well, the rubric is pretty simple. One way to do this is to pick the W that maximizes the probability of the data. Right? So every W is going to give you a chance of seeing those labelings, any labelings, right, independently of what they are. So you want to pick of all the W's, the one that maximizes the probability of the data you're seeing. That's right here. It's a very simple expression is all I want to say. And I do want to point out that solving for W in this equation may look painful, but it's a convex problem. I'm happy to explain it offline. And we can solve this when you have O's into the billions. Say, well, how am I going to get a billion of labels? Get them from the crowd, get them from any noisy source, get them from distantly supervised sources. There's tons of places you can get labels from and learn from them, essentially. The point that I care that you take away is that it doesn't matter. This is not a scalability problem, okay? Except for very, very, very high-end applications. This is something that's going to fit in here. Not a big problem. Why is that important? That means that all the stress, all the problems goes into defining those feature functions, each one of those FIs, making it fast and making sure that they're the right features and checking how well your quality goes. That's the loop that's critical. Learning this function, W, that's not hard. So let me give you one concrete example of how this is used. So here's a predicate we have. It's actually called entity link in our system, so I may slip, but this is, I'm calling it formation link to make it more clear what's going on. So basically, this is a binary predicate that says, does string X map to a known formation Y? And only the XY pairs into a relation be in this record if actually X maps to Y. Okay? This is the first step of any kind of higher level reasoning from text. You want to take the strings that you have and map them to a database of entities that you know about. Okay? So that predicate, each one of those pairs is basically going to be a different argument, a different object that we're going to classify. So the objects of these pairs of strings, or sorry, strings and entities would be more correct. They're usually filtered in some way, like you don't consider absolutely every string on the planet. You have some stupid heuristic that says, like, I only want to try nouns, or something like that, or names and numbers. What do the features look like? These are the actual features, okay? So there's a couple more, but they're very similar to these. They're linguistic features, like, is X a noun? So that's like some kind of signal. If it's a verb, probably not going to be a formation. Is it a direct object? Is it used in some particular grammatical construction? So for context, that's important. Okay. The point is these features are basically isolated from one another. They don't say crazy things about other features. Is X approximately mapped to something in a dictionary? Is X a kind of Z that I know about? Like, is it in a list? You can imagine how you'd write 3-line, 4-line Python scripts for each one of these. There's some things about context, which I'll come back to. Context seems like it should be very useful. We'll come back to that. The labels that we acquire, the geologists right now are actually going through and hand labeling a bunch. It's actually not that expensive to acquire a couple hundred labels, I mean, especially if you care about the answers. You can also do things with crowdsourcing. We do a bunch of stuff with crowdsourcing. You can also do things with distance supervision, where you use the structured database to actually bootstrap for you. I'm happy to talk to you offline. We have a couple papers about doing some of these things. It works really well. You basically use the structured data to generate synthetic training examples that are somewhat lower quality, and you can do this automatically. So I'm happy to talk about it. So all I really care about here is logistic regression is a workhorse. The thing I showed you, as simple as it was in 2 slides, is actually very, very widely used. It's like the first technique that everyone uses when they model these things. Scalability is really not a problem in most of the applications that we have, or at least a class of large, interesting applications. There are people right now who are working on scaling up logistic regression to huge sets of data. Our group does some of that stuff too. That's for really high-end applications. Okay? So most of the stuff that we're using it for all fits in main memory, or you just buy more RAM if it doesn't. The features, though, are absolutely critical. That's the thing that makes it go. How quickly we can get that knowledge and information into the system. And I should also give a disclaimer. There are more sophisticated models, there are things, but in my opinion, the margin on using them is relatively low. So if you're going to build one of these things and start with logistic regression and build the system. There are more sophisticated things to do. There are reasons to consider other things, and there's great machine learning going on, but this is pretty good. All right. So with that, what I want to tell you about is try to make the plea that I have a little bit more concrete and tell you about three challenges that I see that really I hope are related. They're certainly related to sort of data engineering kinds of tasks, and maybe you'll see are related to some programming languages tasks that are close to your heart. A lot of my thinking on this was, I should give credit, is formed by talking to my student, Kumar, who's a great thinker, great guy, and also my buddy Mike, who's a professor, Mike Caffarella, who's a professor at Michigan, and we tell jokes on the phone a lot. But we also came up with some of this stuff. All right. So the three challenges. The first challenge, grunt work statistics. Okay, so basically what I'm looking at here, as I told you, is the machine learning is really fast, but the whole cycle that everyone's going through around that challenge is a pain. I'm going to walk through the 3 steps that I see that I watch my students do again and again, and that published reports talk about again and again. And each one of these, I think, is actually a challenge that some piece of it is a data engineering or also sort of programming languages challenge. So the first thing is when we started this, let me walk through the grunt work statistics needs. We had about 20,000 papers. We had some dictionary of places. We had a bunch of geological reports. These were all stored in a huge number of formats. They were stored in databases, files, key pairs in HDFS, XML, so on. But we had no idea about a huge number of things. And we had to figure out sort of rough statistical estimates of what was going on. So we had to figure out things like just grunt work stuff, like file formats, what fields are in a table. We had to figure out the distribution of tables. As you show, we were extracting carbon. We didn't know if that was going to be high value, or there are a lot of tables with carbon or a few tables with carbon. How many formations are mentioned? Is it just one per table? How many are mentioned in the document? Which dictionaries are relevant? How much do they overlap with a particular corpus? Now, this problem is a pain because most of your development time actually sinks into using ad hoc scripts for each one of these tasks. So someone is sitting down and they encounter a new data set, and they start writing immediately some Python script that's going to figure out what format it's in. Okay, I parse that format. They start doing counts, rough statistical things. And it's all wasted time because it's the same operations every time they see a new text source, every time they see a new table, so on. Now, one hope, actually, of something that I think this one connects up to stuff that people here have done, is stuff like pads++. Right? So if you're not familiar with pads++, it can basically give you a way to introspect on a lot of different file format issues, right? And be able to learn automatically what the data source is talking about. And those kind of techniques are things that we borrow all the time. This addresses some portion of this grunt work statistics, but there's a whole bunch of other things that are on top of it that aren't just informative. As you start to look through and start to build things, you start to now build your own kinds of data structures, your own kinds of entities. And you want to be able to query about them pretty flexibly. Right now, we have like sort of a best practices. We have no kind of system that figures out how to do this automatically. But clearly, to me, solving this part of the problem is a big part of making feature engineering easier. A second problem, which is more difficult to come up with a system for, but is clearly a problem, is what we call unknowable specifications. So when we were talking, I'll tell you why there actually is one system shown here. So geologists know all kinds of interesting things about their literature. So they know things like simple syntactic things, like a formation is shortened after its first use. So they'll say things like Waldron Shale formation, and then in the rest of the article it'll become Waldron Shale. Now if it goes the other way around, it actually means something different, like Waldron Shale comes in. That's a nice, easy rule to encode, but we wouldn't know that. They also know sort of semantic things. We're looking for carbon. If you see the phrase black shale, that actually indicates carbon content in rocks. That's not something that a graduate student would know. Now, it turns out that it's more precise than just there's some carbon around. If you know it's black shale, and you know it's in a narrow band of carbon, if you can predict how much, so how thick it is, you can actually get those TOC measurements like I showed on the earlier slides. Another bit of pain is that the names change over time. Geological ages, it's a flexible science. As they decide they're going to change some stuff, and it changes. There's nothing you can do about it. So the literature refers to one thing one day, and the next thing another day, and you never disambiguate them because you would have no reason to believe they're the same thing. Or you put them together and they're actually not. They're now viewed as two separate things. So there's a bunch of issues. Now, CS grad students don't know any of this stuff. So you say, well, how does that make it actually a technical problem? Because all these things just seem like, well, that's in the geologist's head. All I'm arguing is that there's technical support that you can give to make this process easier. So the hope is really to show them, and this is how all we learn, just show them the mistakes. The fact that our pipeline was so fast that we could have a meeting in the morning, be able to run the extractors, and then in the afternoon after Shannon comes back from lunch, here are some examples of what we changed. These look right or wrong to you. That pipeline where we get the movement like, oh, you're systematic in making this error. I'm seeing this everywhere. This is actually what's going on. That conversation really can be facilitated by a fast extraction pipeline. Now for us right now, we have a very scoped set of extractors that we know how to write, so we can scope this. But in general, how do you turn those things on? The last one is probably the curse of machine learning. And that's the one we call unexpected failure. So it has all these great features where you can just loosely couple and throw all kinds of things in. But the unexpected failure one is that you may think something's a phenomenal idea, and it turns out to be terrible. Okay? So here's one case study of when this happened. So to make this more precise. So developers had to match something that said, here's some strings, match it to those polygons, those units on the map, right? We saw it doing this earlier. So they would have things like, it's near the Allegheny River, and they have to figure out, oh, that's actually this polygon, not this other polygon. And that's not always well defined. So they wrote some heuristics, some simple string matching, like if a town is mentioned and that town is in the polygon according to something. They used some gazetteers where they were actually able to get lat longs for some different things. Then they would match very simple baseline heuristics, the things you would come up with in 5 minutes. Now, one unnamed developer was like, oh, I know the answer to this problem. And they had a very sophisticated pipeline, this NLP aware, where we were going to figure out all kinds of different sets of context, as I mentioned, context. And we don't need to evaluate this until it's next. It's going to be such an awesome feature. Okay? So we're going to figure out the context that it's mentioned in. We're going to store in some nice push-down kind of automata, who was referred to last, all kinds of things like that. The bottom line, in the way I'm setting it up, it was basically 2 weeks of wasted effort. No intermediate state was checked. And even though it seemed like a great idea at the time, the fact that we couldn't iterate through that last loop, that evaluation part of the loop, was killing us. Okay? And this may sound like a strange story, but this is actually when we decided that we were going to have those nightly evaluations that we're going to run, like you commit and check in, give me the quality numbers, and spit into that weird spreadsheet that you just saw that was backing the time. And that's because closing that evaluation loop, we argue, is one step towards fixing this problem. Because you have what you think are great ideas, but the statistics tell you otherwise. So debugging is also another challenge. Now, also throw on top of this, many of the challenges that people in this workshop know much more about than me, so I'm not going to mention. You're having things where you're talking across a bunch of different data processing systems. You saw our horrible mess of slides from before, of what we were dealing with. We have different programming languages. One guy wants to write in PHP, some's in Python, some's in Perl. There's a bunch of C code, Java code. There's all kinds of nasty crap going on that's slinging data around. And there's also a host of traditional software engineering issues. So with that very morose note, I'm going to tell you our vision for just one slide of how to fix these issues. Okay? And this is not to approach a solution. This is just some way that we've started thinking about these problems. And it's our best cut. And this is meant to just stimulate discussion for people to jump in and say, that's a terrible idea. Here's a better way to do that. So basically, we see the developers, as I said, cycling through this loop that has 3 stages, 3 E's. The first stage is this explore the data set. The first task they have, data set shows up. They know that there's new signal in it, like we download the USGS signal, there's something clearly relevant to geology. We just don't know what it is. We don't know how much of it we can use. So there's this exploration where they have to figure out the format to actually acquire the data. Now the thing is as the system progresses, this loop becomes more and more complicated because you have to figure out information that you sort of don't already have or how that information relates to all the data sources that you've already acquired. So there's sort of the traditional data integration headaches. Then there's a challenge which a lot of people have focused on for a while, which is once you've figured out what the heck you want to extract, how do you actually write the code to do it? Okay, so there are tons of IE tools and all kinds of scripting languages. The only twist here is that we can repurpose a lot of the machine learning stuff. If you're aware of things like semi-supervised or unsupervised techniques, which are great phenomenal techniques that people are working on, instead of using them just to test how well do we do, we can use them as recommendations. Sort of imagine, if you imagine like sort of an IDE that's recommending to you which extractor should you write next. A second thing is because we have this very loose coupling property, the person who wrote that extractor could be somewhere else entirely, some other different organization inside the company who's already faced something similar. You can just throw that in there without worrying about damaging your system. Okay? So you don't have to go and learn all their APIs, you just have to learn roughly what it's doing and see if it gives you a valuable signal to complete your task. And finally, we have this phase where we want to evaluate the changes. And this is the thing that we learned the hard way, which was that the longer we delayed evaluation, the more time we were wasting on features that never went in. And so what we wanted to do is fail fast as quickly as possible, automate all of the testing to generate those weird little reports, which actually are quite important for people to see they're making progress on these weird systems that are doing something they don't quite understand. And then be able to display that information. Okay. All right. With that, I'm going to tell you just for 1 second, 2 other applications that you may find interesting, just in 1 minute each. The first is that we're applying the same thing to this thing called ancient books, which is all the OCR of all books published in the UK from 1700 to 1900 with an English professor at UW, Robin, and basically doing deeper statistical analysis. This isn't the same sort of take a commodity database and do an analysis on it, but there's an overview there. If there's interesting data that you want, please contact me. Another collaboration we have, so another place analytics are used, are things like IceCube. So IceCube is a neutrino detector at the South Pole. It's a 30-something country project, $400 million, huge NSF thing, they have their own building on campus. It's a gigaton of ice, it's about 2 kilometers long, it's at the South Pole, and it's meant to detect neutrinos. They had a very sophisticated model on the ice there that was actually used to detect neutrinos. But actually now our code, which is again, I don't have time to go into details, but basically doing this very simple look at the data, simple data filtering, very simple, robust statistical model, is actually in use there. So they replaced their code with ours. And it's a great work by my student, and Ben and I both code by Mark Wellens. And it'll be used by next year to detect 100,000 neutrinos out of about 100 billion events. So 3,000 times every second, they're calling his little inner loop. And the difference, the critical difference was treating it like a feature engineering problem rather than treating it like a physics problem. So this is some hope that these ideas can have impact. So to summarize, the thesis of all this work is that the next breakthrough in these data analysis algorithms is not an individual data analysis piece. It's really, we think, in the ability to rapidly combine and deploy the existing algorithms. They've sort of gotten to that maturity step. This is not to say that there's not great work going on in machine learning, there obviously is. There's a bunch of very cool stuff happening there, and it's advancing very rapidly. But the low-hanging fruit, or a lot of low-hanging fruit, especially for people with our set of skills, really is in this combining meeting. So the final part of the plea is please, if anything in this talk, any piece of that pipeline becomes interesting to you today, tomorrow, next week, next month, next year, send me a note. We'll be happy to expose every piece of it. Everything we do is able to be downloaded. All the code, all the data. Sometimes, our collaborators don't want things being released at particular times, but as long as they're being released to CS people and not competitors, we don't care. So please tell me. And there are also video overviews with that creepy Siri voice of almost all of our projects. So please pitch in and help wherever you want. And finally, thank you to our sponsors, which we can focus on this. Thanks so much.
Thank you very much. So thank you very much, Chris. So any feedback or questions from you guys? You were mentioning this E3 vision.
Yeah.
And I think one side earlier you mentioned that you would benefit from a fast extraction pipeline, so because immediate feedback to the domain experts and so on.
Right.
So how fast would you like to have a real-time thing, or?
I think that's a great question. So the entire pipeline, of course, if you have humans in the loop, they can only look at a small fragment of data, right? So you need to be real-time. We think, we don't know, but we think you need to be real-time on a very small fragment. So you can hold in memory a couple hundred gigs of data, and you're sort of querying on that and getting answers. Now, and then you can run the rest as batch. The problem, of course, is what if you haven't picked the right 100 gigabytes of data or the right amount of main memory for data? And that's where the challenges are that we don't know how to solve. So if you start asking, our best guess right now is if you start asking queries that indicate to us that you're going to be, looking at some relevant information, we can try and bring it in so that it's as fast as possible. But that balance is difficult. The thing that makes it difficult, different than just running an extractor fast, is this sort of interactive, sort of session-like behavior that you can have. And that's something we're interested in, we're working on, we just don't have any ideas how to solve.
I'm thinking of one concrete system that the name escapes me currently. It's meant to show you a screenful or a few screenfuls of data and interactively manipulate it, and then indicate.
There are a couple. There are a couple of that are doing this for structured data, like Tableau kind of does this for structured data. There's not one that I know about for unstructured, totally unstructured data. So definitely there's a bunch of smart people who have worked on things like, I think there was another Blink demo that happened recently where people were able to do this for like OLAP style queries. So people have definitely worked in related spaces. It's not that this is coming out of that field. The thing that I think makes it just a small twist, and maybe not, if there's something out there we can pick up that'd be great, is really the fact that you're dealing with really unstructured data that comes from a wide variety of sources. It's not the traditional business reports. There isn't something that I know about in the BI space, is where you would kind of think that they would have these kind of tools. But there they tend to be more monolithic of building the pipeline into. Yeah, it seems like an interesting challenge.
Okay. Yes, please.
So among these tasks that you listed, like extraction and exploration and so on, where does the time go really? And is it like spread, or is there some task that is really more intensive in attention?
By far, it's explore. So all these kinds of systems that are talking about how do you get a handle on the data, how to you can think about it as almost mining. That seems to be, figuring out what you want to write is the hard part. Now, second to that is once you have that in your mind, actually express it. And there are a bunch of interesting things about the fact that people will express it. Once you have tens of people, will naturally express it in a bunch of different ways. And so I think there's some sort of PL-ish kind of challenges there about, you have different languages and even different data sources to extract the same signal that you would like. The evaluation, when we started, we didn't have as a first-class citizen, and so that cost us a bunch of time. So we think the only thing that we think is interesting there really is that by having an explicit, like, evaluate as fast as possible, we can catch some problems. But yeah, by far it's this extract, figuring out, data debugging really is what it is. People have studied this in all kinds of guises. Chris Olsen had that great work about data debugging and synthesizing for MapReduce a couple years ago. It was a Sigma 10 or Anderson. And these sort of large-scale data debugging things, we're trying to build on that one. But that's where the time is.
James.
So you mentioned that you were looking at using kind of data log-like formalisms for Python, which you guys would prefer from the kind of software engineering point of view, I guess, and the geologists were using PHP, and I can think of lots of other things that people might be using. I'm curious if either there's any lessons from the point of view of language design, or if there's a kind of clear interface that, if you're using these different languages, then hopefully there's a kind of you can sort of say, well, the input is this and the output is that, and whatever you do in between is your problem in designing features. And then, you can imagine taking whatever language you like and plugging it in there.
Right.
So I'm curious, I guess it's not really a clear question, but I'm just kind of wondering, how expressive does the language that is doing that need to be? Does it really need to be a general purpose language?
Great question. So I don't know if it needs to be a general purpose language. My suspicion would be no.
Maybe string processing and a little more, I guess.
Yeah, exactly. So that would definitely that would capture some large fraction of the processing. For us, so to answer your question differently, our data model is very similar to what you described. It's basically maps between basically relations. There's some ways you can introduce order, but basically because we're biased by being database people, basically relations to relation maps. Now, of course, we have some limited support for aggregation that's kind of hacked on, but it's exactly that, just maps expressed however you want, and then we wrap around it. Now, that limits substantially the kinds of sort of performance optimizations we can do, especially across the pipeline, because they're basically these opaque functions that are happening. So if we had them expressed in one unified way, that would be very helpful to us. Now, it turns out for these sort of small-scale applications, performance hasn't been a challenge, so just having opaque things is no big deal. And also what was surprising to us is it turns out that a lot of the feature recommendation things can be done just on this map, because the statistical processing is really only looking at the map, the output of the relation. So you can do almost everything with the data without the structure of the code. But that's one place where clearly we are impoverished. We have almost no knowledge of what that code looks like in our
Yeah, and I guess I'm kind of asking because, from my point of view, the interesting thing to do would be to sit down and look at the kind of features people are actually writing and try and, look where the bugs in the feature code often are, and, try and come up with a language that lets you express the kinds of things that you really want to express very easily without kind of forcing you to contort yourself to do things that are going to be problematic. But I'm not sure if that's really where the time is going. It sounds like the time is really going towards figuring out, once you've got the code, does it actually match the data well?
No, I think so here's one example that supports your position. So we had a bug that was in our pipeline, which was basically that we weren't doing the longest match in one particular piece. So there was some particular way we were matching formation names and strings that was causing a huge pipeline throughout. And it turned out to be a very classical sort of off by one error in a script, right? Now, had that been exposed in some proper way, that would have saved us a tremendous amount of time. The thing that I think would be interesting and potentially novel about this framework, I don't know for sure, but would be if you could figure out how to tie that to the kinds of errors that you see statistically. So here, rather than observing sort of a program trace or some kind of thing about the bug or some kind of bug report, you're instead observing some statistical phenomena. If you could go back and introspect on the code, that'd be pretty amazing. Now, as to what people are actually doing in their features, they do relatively simple things. They're things like, I'm going to sling together a dictionary and match against them. I'm going to write regular expressions and match against them. So when you ask, do they have a constrained set that they're working in? Yes. Do they think they have a constrained set? Is always no. But if you really look at what they're doing, there's a core language that you could abstract. One thing even on the other side, one thing we tried to do was also to understand what a formal data model would look like in this sort of data logic sense, where you would sort of crisply separate out, so you can say things about being well defined. It does have a unique minimal model under the following assumptions, even statistically and all that other stuff, which is one property of logistic regression gives you automatically. We made some progress there. There may or may not be a pod submission depending on how much time my co-author has at it. But yeah, I think that whole area is one that we sort of, on the theory side, just nailing down what these people are doing and giving a principled model to it is really wide open. And I think PL people would have a great time there because the problems are, they're not just about the data. If we model it, it's going to